Hello, this is Kevin Sigwart again. If you missed any of my earlier presentations, I'm the Director of Solutions at OneSpatial Inc. OneSpatial Inc. is a U.S. company that is a fully owned subsidiary of OneSpatial Group in the UK. At OneSpatial, we focus on data management solutions to improve data quality of large complex systems. We use validation, integration, automation, and our rules-based approach to build strong data infrastructures, leading to better outcomes and making your data smarter. This is part 3 of a 3-part series on how OneSpatial addresses data management solutions for clients in our facilities management vertical. If you are interested in learning more about how OneSpatial works with a variety of different clients within facilities management, please watch the introductory presentation to this series. This webinar will be covering OneSpatial's solutions in performing CAD integration projects. Without the proper tools, migrating facility data into a GIS can be very tedious, expensive, and time-consuming manual projects. This typically leads to only doing one-time migration projects, causing the data to get out of sync extremely quickly. This presentation will show how using OneIntegrate's workflows can automate most of the migration from CAD to GIS, which can enable the synchronization between disparate systems like CAD and GIS on a more regular cycle. We will cover 2 different workflows, one being the positional accuracy improvement project, where the CAD data is somewhat spatially referenced, and by using OneIntegrate in a rules-based approach, we can infer shift vectors, validate those shift vectors for conflicts, and then rubber sheet the data in an automated workflow. The second workflow will cover a more complex use case where the CAD data is not spatially referenced, but there is a unique identifier within the drawings to help determine where the drawing is spatially located. Then using geospatial data sets, we can shift, rotate, and align the CAD drawings to fit into the GIS. As I mentioned earlier, this is a 3-part webinar series highlighting many aspects of data management within facilities and campuses. This webinar builds on what was in the first 2 webinars. We mentioned in the first webinar that 88% of all data integration projects fail, and one of the main causes of project failure is poor data quality. In CAD to GIS data integration projects, it is imperative that you assess the quality of both the CAD data coming into your GIS and your GIS system itself. The first 2 webinars will cover both of these topics. In the first webinar, covers the work related to the work we are doing at organizations like Google's Real Estate Worldwide Services. We are working with those types of organizations on their CAD data supply chains in relation to asset management systems. We show how we are helping these organizations with implementing automated workflows, leveraging OneIntegrate and One Data Gateway technology stack to auto-validate and clean the data to ensure the data is fit for purpose when going into these asset management systems. The second webinar is around facilities management within a GIS-based system. We show how organizations are using OneIntegrate to validate their GIS system to make sure the geospatial data sets are spatially accurate, including topology, and validate the attribution. Not only are the GIS systems validated, the GIS can be cross-validated with the asset management system themselves. However, I'm sure many of you have already watched these 2 webinars and you are ready to hear about how OneSpatial can help with CAD to GIS integration projects. As I'm sure you are aware, migrating CAD into a GIS can be quite challenging. There are many pitfalls. After you've gone through and addressed the data quality challenges when dealing with CAD to GIS integration projects, there are still many more challenges that need to be considered. For example, in many cases, the CAD drawings are written in paper space and not in the geographic coordinate system. If you try to add the drawing into a GIS, you will notice the drawing will end up off on Null Island, out in the middle of the Atlantic Ocean. In some cases, you may get lucky, and a world file, also known as a WLD file, will be provided, which will attempt to transform the drawing into a GIS. But it only gives you 2 reference points. And as you move away from those 2 reference points, the drawing gets distorted and will not align to the GIS. And even in cases where the GIS data may have been created using some sort of coordinate system, it still in many cases will not align to your GIS data. Then another challenge is the CAD drawing may be a schematic representation meant to help someone to provide guidance in servicing an asset as opposed to being spatially accurate in order to perform geospatial analytics like tracing, space management, and indoor navigation. In the past, to integrate these data sets, someone may try to manually georeference and then digitize the drawings. Trying to do this manually can be very time consuming, prone to human errors, and will not scale as an organization grows or wants to include more assets. Other organizations use integration tools that can ingest large number of CAD drawings into their GIS. However, we typically find that this is a one-time and a one-way push. Therefore, if the CAD drawings are updated, and in many cases those are the actual source of truth, the GIS will become stale and out of sync with what is in the real world. There needs to be a better way to perform these integration projects that can be run on a scheduled basis and will keep the GIS data up to date within the CAD drawings. There are two different workflows we will cover in this presentation. The first workflow is when we are dealing with CAD data that has georeferenced information. In these cases, we use OneIntegrate to first perform matching or change detection workflows to identify like objects between the drawing and the GIS data. We then have an algorithm in OneIntegrate that will generate shift vectors and anchor points to identify where the data needs to be shifted. We then run our positional accuracy improvement algorithms to align the data sources, and then we can push those changes into the GIS database. The other workflow is a bit more complicated. In these use cases, the data may only be in paper space, and there could be thousands of assets. It is not feasible to georeference all these drawings manually. However, we can use rules-based alignment within OneIntegrate to look at any identifiable information within the drawings or associated metadata with the drawings and use that information to identify matching locations within the GIS. We then can perform shifting, rotating, and alignment model runs to determine the best fit. Then those changes can be applied into the database. For the first demonstration, we are working with a client that has an existing GIS database that only included the room data. They got a new requirement to add additional information into their GIS to include things like stairwells, interior walls, and doors. They had access to the updated CAD drawings from the engineers that were the most up-to-date information for each floor plan. However, when they attempted to add the drawings into their GIS, they found that the CAD data did not align to their GIS data and that some of the rooms had been modified. There was some construction where the rooms were combined into a single room, or other cases where one large conference room was converted into offices. So now they had an added challenge to not only add in these new assets, which is going to be challenging due to the alignment issues, but they also needed to update the room information to reflect what is in the drawing. To work through these challenges, this client worked with OneSpatial and used the OneIntegrate toolset with its change detection and PAI workflows to perform this integration. Also, now they can do this on a more regular basis to keep their data in sync with their GIS. So let's take a look at how they accomplish this. Alright, so let's first, before we do any sort of integration processes, let's first take a look at what the data that we're trying to work with actually looks like. So to do that, I'm going to first open up ArcGIS Pro. And in here, we can see in my map, we have three layers that are showing. We have my interior spaces, which are the rooms. We have our floors, and we have our building footprints. If I dive in and take a look at what is an actual room, we have attribution here that identifies the information such as the space type, what type of access it is, and so forth. And we also have a unique identifier. What is important here to note is that there is a lot of metadata that is in the GIS that may not necessarily be in the CAD drawing itself. So when we're doing these integration projects, we can't just do a clip and ship or just delete all the old data. We're going to lose all that rich metadata. This is why it's imperative to do some sort of change detection first and then only address those changes when doing the integration. Alright, so let's take a look at the actual CAD drawings themselves. So we come over to our FME product, which will give us a way to visualize the CAD drawings. Here I have my CAD drawing itself, and in the CAD drawing you can notice that we have a whole bunch of information inside that drawing. We have information on the actual rooms, but we also have those additional features that we were interested in, such as the stairwells, the doors, and the interior walls. So let's take a look at what happens when we take this CAD drawing and just bring it right into the GIS as an overlay. Let's see how that works. So we come over to back to ArcGIS Pro, and let's go back and zoom back out to the campus level, and let's turn on the CAD drawing that we added. So this is the exact same CAD drawing. You just drag and drop that CAD drawing into the GIS, and we have most of that information that you saw in the FME product. But let's take a look at, what are some of the issues that we may be having. So if we zoom in a little bit, we're going to notice that things aren't quite aligned correctly. We have some alignment issues. So another reason why we can't just add in these features, they're not going to be aligned within the GIS where it's supposed to be. And very likely these drawings or these rooms and these footprints were aligned to align with the actual base map, so it all looks like a one contiguous data set. So we need to first address some of this alignment. And in order to address the alignment, what we're going to do is a series of matching to determine how to do the shifting. What features are a match between the different rooms. So let's go back out and zoom to the campus level. So what we're going to look at is, I only want to look at my actual rooms. So I'm going to turn off everything else besides the rooms. So here are all my rooms in the CAD drawing, and here are all my spaces in the GIS. So we should be able to do some sort of matching to determine like spaces between these drawings. Now we know that the two data sets are not completely in sync because it's been some time and this CAD drawing has been updated. So we're going to have to also take that into consideration too when doing the change detection. So let's go ahead and take a look at how we actually did this inside of the One Integrate product. So I highly encourage you, if you haven't already seen the other presentations, to watch those presentations. We'll give a little bit of a deeper dive into the One Integrate product, but just to give you a high-level refresher, just in case you forgot or you just maybe missed that piece, One Integrate is a server-based solution, and we are right now in the configuration environment, which you can access through a website. Notice that anything that we're doing here can also be automated through the REST API. And basically the way that is organized is you have sessions, which is where you set up all the parameters on what you're connecting to, which validation checks you want to run, what type of cleanup or what type of integration you want to run. All of that is done inside the session itself. Now to configure the data sources that you're connecting to, that's where you configure the data stores. Rules are the validation rules that you're going to run against the data. Actions are what you're using to either correct an existing issue in the data set, reporting on issues, or even doing things like change detection or positional accuracy improvement. And then an action map is how you tie a rule to an action. And if we take a look, we have 3 open data tasks. So we're going to connect to 3 different data sources. The first data source is that CAD drawing that we just looked at. So let's take a look what we're using. We're going to bring in the CAD drawing. Notice the data store types that we have access to. In this case, we're connecting to that DWG drawing. It's going to bring in all the information, such as all the different levels that are associated with that CAD drawing. If we take a look at the campus data that we're bringing in, this is the information that we showed inside of ArcGIS Pro, like the building, the floor plan, and so forth. And then we also have a helper database where we are building the shift vectors, we're building proposals for change detection, things like that. And this is mainly used for demonstration purposes so that I can show you what we're doing and how we're doing the change detection and how we're doing the shifting. So that's why we're bringing in this particular data set. So let's go ahead and fire this off. So basically what we're going to be doing is we're going to be first opening up the data sources, so we're going to connect to the CAD drawing, and it's going to bring in all of that information, all those different levels. We are also bringing in my campus data, so all the information for the campus. And then we're going to run through just some cleanup, essential geometry cleanups, because typically we find issues with CAD drawings, so we make sure we clean those up. But the next rule we're going to run is we're going to make sure that, how are we matching our CAD data to the GIS data? Do we have matching rooms? And what I found is that for every single room that's in the CAD drawing, I'm getting a 90% conformance ratio. So we're seeing here that of the 246 objects in the CAD drawing, we found matches for all but 23. So let's see some of the reasons why we're not getting matches. So let's go ahead and view the map viewer inside of OneIntegrate. And what we're going to do is, because we're going to be only looking at a few layers, let's just turn on a couple layers that we're interested in. And then we can take a look now at our matching rooms. So this is the first one that we don't have a match. And if I select my features, I can see that the CAD drawing is one feature here, but in the interior space there's two. So what happened is that basically somebody knocked down this wall and turned this into one feature. So this is why we can't, in the matching piece of it, we can't do shift vectors because we're comparing non-like geometries. In this case, in the CAD drawing, there are spaces that are containing other spaces. So kind of like the gross area, similar things like a gross area. So we also need to ignore these particular geometries too. And then, here's another example. So another example of where there's multiple geometries. So we can address all these particular issues and then perform the matching. So that's what we're going to do next. And what we're basically going to be doing is we are going to be cleaning up, first of all, flagging when we know it's a room versus a non-room. So a room, it basically means that it doesn't have another geometry contained inside of it, another room inside of it. Otherwise, it's a room containing other rooms. We're also going to then also pull the information of the room ID from the actual CAD drawing into the each individual object, and then we're going to then do my matching. So what we're doing matching is not only we're going to do matching for where the geometries are similar, we're also going to look at the IDs. So when we do the matching room, we're getting a 95% conformance. So we went up from something like, what was it at? We were at 90 to 95%. So now we're only seeing the differences where the actual rooms have actually changed. But then we're also seeing, what's interesting is some of the identifiers have also changed, the space IDs between these two things. So that's an interesting thing that we're going to also need to take into account when we're doing our change detection, is that we also may want to apply those new IDs to our rooms in our GIS to make sure that our GIS stays in sync with the CAD drawing. So let's go ahead and next we're going to do the change detection. So basically what the change detection is going to do is it's going to determine, where do we have matching rooms, where do we have different attributes for matching rooms, where do we have some sort of, where the geometry has been updated, or where do we have adds and deletes. Now to visualize this, I'm going to go back to my GIS to just show you the change detection that we're performing. So we're going to go back and flip to ArcGIS Pro and look at those results. So go ahead and open my map up. And our output is going to be the change detection proposal layer. And this is identifying all the changes that are in the data set. So matches are what we're concerned about for dealing with doing the positional accuracy improvement. This is what we're going to build our shift vectors using. But we also need to apply changes in our database based off of, if there's any sort of change in the geometry of the room, or if there is any sort of attribution, or if a new room has been added or deleted. So let's take a quick look at examples of some of the changes that we have. So here we're flagging a scalar change, and if I select this particular feature and look at the attributes, so in my building interior space, the identifier is this particular string. But if we look at the actual CAD drawing, that has a different value for the, and actually in order to see that I need to bring on my annotation. So let me turn on my annotation. So we have a different string. We also take a look at another example here. Now this is the actual restroom. If we look at the restroom itself, in the CAD, in the GIS, it is identified as men's with a apostrophe, and in the CAD drawing, it is not plural, it is just men. So that's why we're flagging that as a scalar change. The geometries are close and similar, but what's different about the two is the attribution. But now let's take a look at where the actual geometries have been changed. So in this case here, we're flagging a reshape and a delete. So if we look at what happened here, and let's select all the features. So what we have here is we have a spatial change for this geometry, and we have a delete in this particular geometry. And basically what is happening is this is the new geometry. So this geometry has been extended because this wall has been knocked down and made into one room, which means the old conference room was deleted. The old room here was deleted. So this room was deleted, made into one large conference room. The next example is kind of the reverse. This is where we have a reshape and an add. And in this case, what happened is we had two rooms in the GIS. We had one room in the GIS, and then we had two rooms in the CAD drawing. So basically, in this case, we actually built a wall in here and created a new room. So we reshaped the one because the room number didn't change, and then we created a new room inside. So that's why we're flagging that as a spatial change and an add. But as I said, what we're really concerned about is we only want to see, at this point, we're interested in the matches. So let's just real quick. Let's only look at our matches. So now we can identify all of our matches. And to do now with those matches, we can then build the shift vectors to determine how the shifting should occur between the CAD drawing and the GIS. So let's go back to OneIntegrate. And now we're then going to build our shift vectors and shift the data. But not only are we going to shift the room data to align, we're also going to bring in the stairs, the doors, and our interior walls and our glass walls and integrate that into the GIS also. So let's go back and take a look at what we're doing here. So as I said, the first thing we're going to do is we're going to build my shift vectors. So let's go zoom into where we had that alignment issue real quick. And we can see we're identifying let me turn my proposals off real quick. We are identifying that the CAD drawing must be shifted at this place to this location, and we have done this throughout the entire drawing. So anywhere we have matching geometries, we've built the shift vectors, and then we can apply those shift vectors to not only the rooms, so that the rooms are now aligned. So we now can align our rooms. So now all of those rooms in the CAD drawings are aligned, and also the proposals are now aligned. But we can also do the same thing for all of the line work, such as the doors, the walls, interior spaces, and stairs. So let's go ahead and just take a quick look at that. So now we've brought in our stairwell, and we turn off my proposals. So now we've brought in our stairwells, we've brought in our doors, and notice all of this is actually aligned to my GIS so that we have properly integrated those data sets, those new features. But what about all those changes? That's what we need to address next. We have those changes. We want to make sure that this GIS information is up to date with everything that is in that CAD drawing. So that's what we're going to do now is we're going to go through those proposals, and we're going to apply those proposals to only update the features that have actually changed. So let's go ahead and do that. And in this case, because we are not actually doing any of the we're only addressing the changes, we're not going to lose all the metadata that was associated with any of the features that already had it. If all we need to do is update the ID, we can just push that ID to update. If all we need to do is realign one of the rooms, we'll realign it, keeping all the metadata associated with that particular geometry. So let's go back and take a look at what we actually did. So we'll go ahead and turn on those changes, and let's go back and look at some of those areas where we had some issues. So where we had that scalar change, we now have updated this to now have the proper code. So now the space ID has been updated. If we go back to where that bathroom was, in this case, we have now updated the room to actually the space ID to be men, not men's. If we go to where we had the reshape and the delete, notice that we've reshaped this. Let me turn off the old one. We've reshaped the geometry now, and all of that attribution that was associated with it has maintained. And then if we go to where we had the reshapes, where we had the reshape and the add, notice that we now have those two geometries that have been created. Or one of them still has all the metadata because it was a reshape. The other one has it's an add, so we haven't populated it all. So we have to now go through and populate all of that information because it is a new feature. So populate with all that metadata. We took all of that CAD information, we compared it with our GIS, we determined what was different. We figured out that we needed to perform some sort of shifting to align the data. So then we built shift vectors. We aligned the data. We brought in those additional assets like the door information, the wall information, and the stairwell information. And then what we did is we then updated where rooms have actually changed since this GIS data set was created. So doing all in automated fashion. In this case, we were working with one floor, but now we can apply this to all of our floors for all of our buildings, and we can do it in an automated way. And this can be done repetitively. So as the CAD drawings change and update, we can then update our GIS and then flag the appropriate workflows of what needs to be occurred after those changes have been committed. The next use case is a pilot One Spatial implemented for NASA. In this case, NASA had electrical manholes that identify the feeder line information about where each feeder line is coming into the manhole, how the feeder travels around the manhole, and where the feeder line leaves the manhole. NASA challenged us to show how we can automate the process of taking a set of electrical manhole DWG drawings, identify all the objects, including the feeder information, identifying the spatial location of each drawing, then shift, scale, and rotate the drawing to fit into the GIS. Then identify each feeder line, the number of times it wraps around the manhole, and where each feeder line is coming and going. The result will be understanding how the feeder lines are distributed through the network, and then be able to leverage Esri's utility network tools to trace the network. The client was pretty clear with us after this project concluded. He told us that he thought we were going to fail. At One Spatial, we solved extremely difficult data management challenges. We were able to break this project into a few workflows, and by leveraging One Integrate and a rules-based approach, we were able to not only accomplish this, but we were able to fully automate the process from end to end. Over the next couple of slides, we will walk you through the methodology, and then we will demonstrate the workflows themselves. First, we had to identify all the objects in the drawing. These drawings were not broken into a list of levels that identified what everything was. We basically only had a level for line work, the wires, and the attribution level. This did not give us enough information to fully understand what each object represents. However, by leveraging One Integrate and its topological primitives, we can infer what the objects are from the schematic drawings. This includes identifying the floors, which is essential in the alignment of the data into the GIS. We were also able to identify the walls, banks, ducts, wires, and feeder information. Now that we've identified the floors, we can use those floors to align the data with the corresponding features in the GIS. To perform the shifting, scaling, and rotating, we use the labels in the DWG drawing to match the DWG drawing with the corresponding manholes in the GIS database. We then shifted the floor to be centered on the GIS manhole area. Then using the areas of both the GIS manhole and the CAD manhole floor, we could figure out how to scale the CAD drawing to be the correct size. Lastly, in most cases, the drawings are not aligned to north. we had to rotate the floor around and validate its fit at each iteration. After we completed the circle, we ran some 100 different combinations and figured out the best fit for the rotation. We then applied the shifting, the scaling, and the rotating amount to all the objects in the drawing. This resulted in the objects in the CAD drawing to be in the right location inside the GIS. However, we still must address that this is only a schematic representation. At this point, the data is not ready to perform geospatial analytics on the feeder lines. So the next step is to run the schematic into the actual geospatial representation. So next, we identify the splices within the feeder lines by finding where the feeder bifurcates. After identifying the location of the splice, we can replace the bifurcation with a straight line, and then we can place a point identifying where the splice occurs in the feeder line. Then we had to identify the feeder information for each individual wire. The drawing contains labels for each feeder line with call-out lines pointing to which feeder each label referred to. We were able to identify the labels and the call-outs that the label was referencing and determine which feeder line the label was pointing to. This enabled us to get the feeder line identification with each drawing. Then we had to take the feeder lines and connect them to the corresponding electrical lines, but also make sure that we were aligned to the feeder lines with the manhole floors. By doing so, we can calculate the number of times the feeder wraps around the manhole and estimate the length of each feeder line. So after we wrote the rules in OneIntegrate to automate the process for one drawing, we then tried to run the same set of rules on all 30 drawings provided. After a couple of minor tweaks in the rules, we were able to load all but one or two drawings into the GIS and connect them all into the network. The reason for a few drawings not completely going through the workflow was related to data quality and standardization with those drawings. These types of issues would normally be addressed before trying to perform the integration, like we talked about at the beginning of the first webinar. The last step is to follow the electrical lines for each feeder as it moves through the manholes in order to build the entire feeder network. Let's now show you the demonstration of how we actually did all of this work on these individual drawings. Alright, so using FME's Data Inspector, we can look at one of these example CAD drawings for the electrical manhole. Notice that it is, as I mentioned before, it is a schematic representation. It is not a geospatial representation. And we only have a few levels in this particular drawing. One of them is the bold text, which is useful because it actually contains the number of what the manhole is associated with. So this is the unique identifier that we can use to identify where in the GIS these two should be linked. We also have a border, which is in this case not very useful for what we're trying to accomplish. We have the manhole, which is a series of just individual line work. And then we have some additional text information that has the feeder information. And we have the wires. So this is the information that we have, and we have to be able to figure out how do we get this and migrate this into a GIS. So let's take a look at what we're actually trying to do inside the GIS to align this. So let's flip back over to ArcGIS Pro. So now in ArcGIS Pro, we're looking at both the CAD drawing itself and the geospatial network. On the left is exactly what you just saw before in FME, but now we're visualizing it in the GIS. Notice that this is actually in paper space. It has no sort of geospatial representation at all. And then on the right side is my electrical network, and I have some information about my manholes. So let's go ahead and just zoom to the exact manhole that this particular example is pointing to. So this is what we have in the GIS. Luckily, we have the actual vault that is inside the individual GIS. And we have a identifier in this point that identifies what the manhole number is. So by using that, we can then at least associate the drawing with the particular vault itself. But what we'll also notice here is that if we look at the drawing is not aligned as to due north. Like the actual GIS is. So not only do we need to move the drawing over there, we're also going to have to shift it to align it to due north. And then not only that is that this is one of these is in paper space and one of these in geographic space. So then we're also going to have to do some sort of scaling also in order to get it to fit. So that's what we're going to do first is we're going to use OneIntegrate to identify what these individual objects are, because right now we don't have enough information to do the alignment. We got to figure out what all these different objects in the drawing are, and then we can do the analysis to do the shifting, rotating, and aligning. So let's go ahead and take a look at that inside of OneIntegrate. So inside of OneIntegrate, we're currently pointing at one of these individual drawings. Later, what we end up doing is we end up automating this using the REST API to point at an entire folder of drawings to do this entire process through that. But for the demonstration, let's just look at one drawing. And in this case, we are looking at that exact same drawing that we were just opened up inside of FME's Data Inspector. And we're going to bring that in, and notice same thing here. We have those 4 levels that we're interested in, and we are going to bring that into OneIntegrate. So I'm going to hit play, and we're going to bring that into OneIntegrate. And what we're going to do is we're going to build the topology, because we're going to use the topology primitives to determine what different objects are. This is how we can identify what the floor is, which in this case is one of the more important pieces. So let's go take a look at what we're looking at inside of OneIntegrate. So let's go ahead and view the map. So we brought this into OneIntegrate. Notice that we have all these individual lines. So we need to use topology to identify this individual floor. So that's what we're going to try to do first. And to do so, we are going to first look at grabbing the different, as I said, the faces of topology, and we can get this individual face. We then can identify any sort of missing features inside that particular floor. And then we actually can join this to where we have the actual entire floor now. Now we actually have my floor. And this is what's going to be used to do the shifting, scaling, and aligning. But not only that, we still need to be able to identify the other individual features, such as the walls, the banks, the ducts, and lastly, we also need to pull the feeder information. If we look at these individual, this geometry right here, notice that we don't have any sort of feeder information associated with this particular call out. So we got to pull the feeder information from this individual point that has that information in it, and we're going to reference that all the way down over to this particular location. So here we have my text string is 2H. So that's what that feeder is referencing. So we're going to go ahead and do that next. And then when I select this individual feature here, we should now have that feeder information. We have that 2H feeder information associated with that. So now that we've identified the objects in the drawing, the next thing we need to do is we're going to have to now do the shifting and the scaling in order to identify where in the GIS this particular manhole is associated with. So we're going to bring in now my geospatial network. We're going to identify the matching manhole volt, and then we can use the algorithms to do the scaling, the shifting, and the aligning. So let's zoom now into the GIS. So now that we're in the GIS, we now can see that we have brought over all of my features into the GIS, and they are all now spatially aligned correctly inside the GIS themselves. Now it's not perfect, but we are pretty close enough in order to get the line work to align to the GIS. So that's what we're going to need to do next, now that we have the data aligned into my actual GIS. So then we're going to pull out all of the wiring information. We're going to connect those wires. We're going to populate the feeder information onto the wires. and then we're going to actually connect the wires to the electrical lines in the GIS, and finally estimate the actual wire distance that it's actually going to move. So if we come back and take a look now at my map inside of OneIntegrate, if I select one of these wire, now there's a lot of layers going on in here because there's a lot of intermediate steps. So let's just look at my schematic wire, and now I have my wire here. Notice that I have my wire, I know where it starts and ends, and to show us that it's actually connected, let's turn on the electrical line coming in. So that this is the electrical line coming in. We're connected now to the electrical line. We also have my feeder information populated for that particular line. So let's go back to the GIS application, and let's see what we did inside the GIS application. So we're moving back to ArcGIS Pro, and just to so we can see what we actually did here, let's go ahead and turn on those layers. So we brought in the floor, as I mentioned before. We have the walls, we have the banks, we have the ducts, we have the schematic wiring. And as I mentioned before, if we zoom in a little bit and we look at these individual wires, right now these wires do not have information about the feeder ID. It is also not properly connected, and it has these weird splices in them. So these all have to be cleaned up. But we were at this point, we were able to at least get this CAD drawing schematic representation into the GIS. We rotated it so it's all aligned correctly. Now with that, let me turn this this off here, and let's now take a look at what we've done from here. So the next thing we wanted to do is we wanted to look at the connecting the wires. So what we're going to do is we're going to then connect those wires. So I'm going to go ahead and turn off the schematic wire. Notice now that we have a actually connected wire that doesn't have those bifurcations. It connects to the individual ducts. We also are missing now my splices. If you notice that we don't have those splices in there. So we want to define those splices as points. So we identify the splice as a point, and we do it actually in the middle of where that particular splice was being referenced. So if we go ahead and select this individual feature, we can notice that we actually do have, not only do we have connected it, we also do have that feeder ID information too associated with it. But this is still a schematic representation. We're still not connected to the actual electrical wire. So that's the next thing we want to be able to do, is connect this to the electrical lines. So that's the next thing that we did. So to visualize this is a lot easier if we turn off some of these layers. So we're going to turn off some of these layers, and we're going to take a look at the schematic representation. So that line that we were just looking at is now here. Notice that we are connected to where it starts here, connected to that particular line, and we now have this line coming through here and coming out at this location. If we look at another example here, this one is the 2T feeder line, and it comes in at this location, it wraps around, it comes out at this location, and wraps around this way. And we did this for all the feeder lines. So here's all of our feeder lines coming and going from that particular network. But we didn't just do this for one drawing. We had to do this for all of the drawings. So let's go ahead and zoom back to another example here. So here was another location, and notice that we brought in all of those feeder information and the splicing and so forth. And notice that some of these are a little bit different. They wrap around multiple times. All of that was taken into consideration when building this particular network. And if we go ahead and zoom out to the full network, you can see we have all of my locations here built in. And the last step that we needed to do was we needed to follow the network for each individual feeder line and trace it along for wherever we have manholes. Now in this case we only have about 30 manholes, so we weren't able to trace the entire network, but we can at least show that we can build the networks. So let's go over to my feeder map. Alright, so now that we're looking at the all the GIS data. We have the manhole vaults, the duct bank areas, and the electrical lines and the electrical manholes. Now for visualization purposes, let's turn off the electrical lines and let's look at the feeder line information. So if I go over to my feeder lines, we could turn on one of these example feeder lines, and this is the feeder line. Notice how we are starting at this particular location. We wrap around this particular manhole. We are following within the bank, along the network, around this manhole, and out along to this other manhole, and we keep moving on till we get outside of my, till we end at this particular manhole. And there's other examples here. Here's another example where it follows a similar path, except it wraps, in this case, it wraps around this manhole and ends at this particular location. At One Spatial, we solve extremely difficult data management challenges, like this manhole use case. We were able to break this project into a few workflows, and by leveraging One Integrate and a rules-based approach, we were able to automate the process of loading the CAD drawings into the GIS and really exceeded the client's expectations. I mean, the client thought we were going to fail, so I'm sure you can imagine how well we exceeded those expectations. During this webinar, we covered a couple solutions on how One Spatial can solve complex CAD integration projects. We showed that there are many challenges in dealing with CAD data. CAD data tends to have poor data quality, and addressing those data quality issues upfront before attempting integration projects is key. We covered in the first webinar how you can validate CAD drawings before even accepting them from the engineers. Also, in performing these integration projects, your geospatial data sets must also not have extensive data quality issues. So for example, if the electrical network had topological issues, it would have been near impossible to connect and create the feeder line information we did in the last demonstration. In the second set of webinars, we covered how you can validate and clean your GIS data. After addressing those data quality issues, there are still many challenges with CAD integration projects, including the alignment and the schematic representations. Within this webinar, we showed how leveraging One Integrate and One Spatial's team of expert rule writers, we can automate the process of integrating these data sources, and even if there are alignment issues and no spatial referencing information or schematic representations. If you have a challenging data management required within facilities management or any other industry, please reach out to us today at onespatial.com. We love to solve complex data management issues to make your data smarter.